a balanced three-phase system, the neutral current is ideally zero. However, systems with nonlinear loads, like those commonly found in data centers, often experience harmonic currents that can cause a non-zero neutral current. The current total harmonic distortion, or THD, of a phase provides a measure of the current waveform's distortion due to these harmonics. A higher THD value indicates greater distortion of the current waveform. When the current THD of a phase exceeds approximately 15 to 20%, the neutral current can become significantly high. A neutral current measurement of 31 amps, while each phase is carrying around 90 to 100 amps respectively, strongly suggests a substantial amount of harmonic current circulating within the system. Consequently, it is advisable to oversize the input or bypass neutral feeder to effectively handle this harmonic current. While unbalanced conditions between the current phases can also contribute to a non-zero neutral current, in this scenario the phase currents of 100 amps, 90 amps, and 90 amps do not indicate a severe imbalance. Therefore, the primary concern is the presence of harmonic currents. It is recommended to oversize the input bypass neutral feeder by a factor of 1.5 to 2. This oversizing ensures that the neutral feeder can safely and reliably accommodate the harmonic current and any potential unbalanced conditions that may arise in the future. When dealing with electrical systems, especially those involving sensitive equipment such as in a data center, it is crucial to adhere to relevant electrical codes and standards to ensure safety and optimal performance. Firstly, determine the appropriate ampacity for the neutral conductor. The National Electrical Code, or NEC, provides guidelines for conductor sizing based on the anticipated load. Refer to NEC Table 310.15b16 or the corresponding table in the Canadian Electrical Code, or SEC, to determine the ampacity of conductors based on their insulation type and operating temperature. Secondly, consider the impact of harmonic currents on the neutral conductor. In systems with significant nonlinear loads, such as variable frequency drives, or VFDs, and electronic equipment, harmonic currents can substantially increase the neutral current. Oversize the neutral conductor to accommodate these harmonic currents and prevent overheating. A common practice is to increase the neutral conductor size by a factor of 1.5 to 2, depending on the severity of the harmonic distortion. Thirdly, account for voltage drop in the neutral conductor. Excessive voltage drop can adversely affect the performance of sensitive electronic equipment. Use voltage drop calculators or software to determine the appropriate conductor size to maintain voltage drop within acceptable limits, typically 3% or less. Fourthly, ensure proper grounding and bonding of the neutral conductor. A properly grounded and bonded neutral conductor provides a low impedance path for fault currents, enhancing safety and minimizing the risk of electrical shock. Follow NEC Article 250 or the corresponding CEC section for grounding and bonding requirements. Fifthly, use appropriate connectors and terminations for the neutral conductor. Ensure that connectors and terminations are properly rated for the conductor size and material to prevent overheating and ensure reliable connections. Torque connectors to the manufacturer's specifications using a calibrated torque wrench. Sixthly, consider using a dedicated neutral conductor for sensitive electronic equipment. A dedicated neutral conductor minimizes the risk of common mode noise and interference, improving the reliability and performance of sensitive equipment. Isolate the dedicated neutral conductor from other circuits to prevent the flow of unwanted currents. Seventhly, install surge protection devices, or SPDs, on the neutral conductor. SPD protect against voltage surges and transients, preventing damage to equipment and improving system reliability. Choose SPD that are specifically designed for use on neutral conductors and are properly rated for their application. Eighthly, regularly inspect and maintain the neutral conductor. Perform periodic inspections to check for signs of overheating, corrosion, or damage. Tighten connections, replace damaged components, and clean conductors as necessary to ensure continued reliable operation. Ninthly, document all conductor sizing calculations, grounding and bonding procedures, and maintenance activities. Proper documentation facilitates troubleshooting, ensures compliance with codes and standards, and provides a valuable record for future reference. Keep documentation up to date and readily accessible to authorized personnel. 10thly, consult with a qualified electrical engineer or contractor. Electrical systems can be complex and potentially hazardous. Consult with a qualified professional to ensure that the neutral conductor is properly sized, installed, and maintained in accordance with applicable codes and standards. A qualified professional can also provide valuable insights and recommendations for optimizing system performance and reliability. In summary, oversizing the input or bypass neutral feeder in a system with nonlinear loads is a prudent measure to mitigate the risks associated with harmonic currents and potential imbalance conditions. By following the above recommendations, you can ensure the safe, reliable, and efficient operation of your electrical system. The presence of harmonic currents and unbalanced conditions can lead to several adverse effects in electrical systems. These effects can impact the performance, efficiency, and lifespan of equipment, as well as the overall safety of the system. Firstly, harmonic currents can cause overheating of conductors and transformers. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency, typically 50 Hz or 60 Hz. These currents can cause increased losses in conductors and transformers due to skin effect and core losses, leading to overheating and potential failure. Secondly, harmonic currents can lead to voltage distortion. Harmonic currents flowing through the impedance of the electrical system can create voltage drops at harmonic frequencies, resulting in voltage distortion. Voltage distortion can adversely affect the performance of sensitive electronic equipment, causing malfunctions, errors, and reduced lifespan. Thirdly, harmonic currents can cause nuisance tripping of circuit breakers and protective devices. Harmonic currents can cause protective devices, such as circuit breakers and fuses, to trip unnecessarily due to the increased RMS current and distorted waveforms. Nuisance tripping can disrupt operations, increase downtime, and reduce productivity. Fourthly, harmonic currents can interfere with communication and control systems. Harmonic currents can induce noise and interference in communication and control systems, leading to errors, malfunctions, and reduced reliability. Shielded cables, filters, and other mitigation techniques may be required to minimize interference. Fifthly, harmonic currents can cause resonance in electrical systems. Resonance occurs when the inductive reactance and capacitive reactance of the electrical system are equal at a particular harmonic frequency. Resonance can amplify harmonic currents and voltages, leading to severe voltage distortion, equipment damage, and system instability. Sixthly, unbalanced conditions can cause neutral conductor overloading. In three-phase systems, unbalanced conditions can result in excessive current flowing in the neutral conductor. Overloading the neutral conductor can cause overheating, voltage drop, and potential failure, especially in systems with nonlinear loads. Seventhly, unbalanced conditions can cause voltage imbalances. Unbalanced conditions can cause voltage imbalances where the voltages in the three phases are unequal. Voltage imbalances can adversely affect the performance of three-phase motors and other equipment, leading to reduced efficiency, increased heating, and premature failure. Eighthly, unbalanced conditions can cause increased losses in transformers and motors. Unbalanced conditions can cause increased circulating currents in transformers and motors, leading to increased losses, reduced efficiency, and overheating. Ninthly, unbalanced conditions can cause pulsating torque in motors. Unbalanced conditions can cause pulsating torque in motors, resulting in vibration, noise, and premature wear and tear. Tenthly, unbalanced conditions can cause inaccurate metering and billing. Unbalanced conditions can cause inaccurate readings in metering equipment, leading to incorrect billing and disputes with customers. It is essential to implement appropriate measures to mitigate the adverse effects of harmonic currents and unbalanced conditions. These measures may include using harmonic filters, power factor correction capacitors, shielded cables, balanced loads, and voltage regulation equipment. Regular monitoring and analysis of the electrical system can help identify and address potential problems before they escalate. Furthermore, it is crucial to adhere to relevant electrical codes and standards to ensure the safe and reliable operation of electrical systems.